All right, welcome back, everybody. This is going to be lecture 26 and also the beginning of topic 6 amines. We should cover all of the amine section today with the reduced content now present. So, most of you are familiar with amines. They have a nitrogen. There are two general types. We have some that are alkylamines. They have a single lone pair. We're not going to focus too much on the nomenclature. Generally, you'll be saying what type of alkyl group is attached to the amine, followed by amine. So if R is equal to, say, ethyl, this would be triethylamine. Again, we're not going to focus on nomenclature. I think you're familiar with most of this from 2311. The main molecule you may need to know is something like Annalen. We've already discussed annalines from back during the second topic when we talk about electrophilic aromatic substitution. And these would be aryl amines, where now we have a benzene ring attached to the amine. Amines are pretty important all along in chemistry. We can find a number of them embedded inside rings. So these are called heterocycles. Hetero means because they are different than all carbon rings. There's a variety of different ones. These are all names which you should know. You'll see that they come in, say, a fully unsaturated pyrrole ring has five points on it with one nitrogen, including this lone pair. This ends up being aromatic. Imidazole ends up being aromatic. Indole ends up being aromatic. And all of these have lone pairs inside the heterocycles that contribute to the 6-pi electron system, where something like pyridine has its lone pair outside the ring. And so this is also a 6-pi system. It's also aromatic, but it does not involve that lone pair in the aromaticity. So you can refer back to the earlier notes on determining these things. And we also have quinoline, which just adds another benzene fusion to a pyridine ring. We should add on another benzene ring, so we have two benzene rings kind of fused together. This is going to be a 10-pi aromatic system overall. Then we have 6-membered, fully saturated heterocycles like piperidine and pyrrolidine. And so these types of heterocycles make up a lot of important types of drug molecules and molecules that are found in the body. So things you may have heard of, things like serotonin, stuff that makes you happy. Dopamine, these are neurotransmitters, as is acetylcholine. You may have heard of, if you've taken, or when you get to biochemistry, you'll probably learn about acetylcholine esterase inhibitors, and there's different ways that we can have mechanisms of actions for drugs that can actually block some of these receptors. And then also a wide range of pharmaceutical agents also contain amines. We can see the nitrogens are present in all of these molecules. This allows for hydrogen bonding within receptors within the body many times, or hydrogen bond donation. So a lot of times amines are key functionalities that will be able to bind to their targets and interact with either proteins or other types of receptors. But again, this is mainly just for reference, a little bit of background. We need to get into the actual chemistry. One of the defining features of amines is that they are basic. So amines always have a lone pair on the nitrogen, and these are able to take hydrogens from acidic sources. So in this case, if it were water, we'd be grabbing the proton from water, creating an equilibrium with the ammonium cation, its conjugate acid. Correspondingly, we'd be making a conjugate base along the way. In this case, it's hydroxide. So when we're talking about basicity, instead of saying something about the pKa or pH or something like this as a solution, we will refer to the Kb. It's the exact same concept describing this equilibrium of protonating the amine to make a conjugate acid. So a low pKb would be something that is going to be very basic, whereas something with a high pKb would be something that's not very basic at all. Frequently, though, instead of trying to talk about things in terms of Kb, chemists will talk about it conversely in the pKa of the conjugate acids. So this is frequently confusing, I think, in the literature and sometimes in textbooks, where someone might say the pKa of ammonia is 9.3, when really they mean the pKa of its conjugate acid. But this also gives us information about the basicity of the parent amine, because the acidity of a conjugate acid essentially will decrease with the ability to stabilize the ammonium cation. So if we look at this, and we can see that an ethyl ammonium salt is going to be the least acidic, that means that the initial parent primary amine would be the most basic. And this will be true across the board. So as you go from something like ammonium to methylammonium to ethylammonium, we see an increase in the pKa of the conjugate acid, and this also will tell us that the corresponding amine would be more basic. So we kind of use this logic. It's good to be able to kind of go back and forth and think about what the stability of this nitrogen is and how that will be impacting either the initial basicity of an amine or the acidity of the corresponding conjugate acid. So to take a closer look at some of these features, we're going to do some problems where we look at two different sets of 3 nitrogen-containing molecules, and it says order them in a series of amines with increasing pKa. Let's change this. Let's just say increasing maybe basicity. That way we'll just be what is the best base, what is the worst base, and I think that way we can get rid of some of these terms for discussion, at least right now. And there's probably about 3 factors that we'll want to be considering when we look at problems like this. Particularly, we want to see if we want to look at things like hybridization. We could look at different electronic effects. And also we could consider things like aromaticity. So frequently we'll want to go and imagine how stable is the molecule or what changes in the event that it does get protonated. So for instance, if we were to use pyrrole as a base and we were to protonate it, is there any significant gain or loss of stability along the way? If we go from something like piperidine, we make its conjugate acid, and finally making pyridinium as well. And so we can go through in this sort of checklist and consider, what has changed and where were these initial nitrogens in their and what hybridization state. So we can quickly see that piperidine is sp3 hybridized, whereas pyridine is sp2, and pyrrole is sp2. So remember, this nitrogen lone pair on pyrrole will be sp2 hybridized because it's involved in resonance, and especially further than resonance, involved in aromaticity. So this will transfer it to a purely p orbital. So we know that atoms with more s character will be more electronegative. That means they don't want to have a positive charge put on them. So right off the bat, we can see that the central piperidine will be the most basic. And now we need to compare between the 2 different remaining heterocycles. We have pyridine and we have pyrrole. So both these are sp2 hybridized. Both of them are aromatic systems. There's not a lot of electronic effects you can see now, but we do see that if you try to protonate pyrrole, we end up losing aromaticity. Whereas pyridine is still aromatic. So that means we would say that pyrrole would be the least basic. It has the biggest energetic penalty upon being protonated, and it also has a nitrogen that is sp2 hybridized. To go and kind of check these numbers a little bit further, we can also go look up the pKa values for these conjugate acids. We can see that pyrrole is 0.4. We see piperidine is 11.2, and pyridinium is 5.2. So this is the trend as we'd expect, where something that is going to be very acidic in its conjugate acid really doesn't want to be protonated very much, so therefore the parent amine would not be very basic. We can use similar logic to go and analyze these different types of annalines and one cyclohexylamine. Now we can actually compare slightly different features of the molecules. All of these are NH2s. The hybridization of the annalen will be closer to sp2 because of resonance. And the other feature is that there's a benzene ring attached to the nitrogen, where here it's a cyclohexyl group. So this phenyl ring right here being sp2 hybridized will lead it to be a much better electron withdrawing group. You can refer back to the group electronegativity chart from topic 1. And this will already tell us that going and considering these conjugate acids, the cyclohexylamine, the cyclohexylammonium, will end up having the most stabilized charge because it has the least electron withdrawing substituent attached. So since we're making positively charged amines, having an electron withdrawing group as a substituent will make the ammonium salt less stable. So we can already see that hybridization will play a role more in a substituent effect, along with a bit of the character of the nitrogen itself. So this will be the most basic. And now comparing the aniline to the paranitroaniline, we already said that electron withdrawing groups will end up being destabilizing to the ammonium salt. That means that it'll make the parent amine less basic because we're going to be pulling electron density. So this is a strong electron withdrawing group. And you can even push electrons of this nitrogen all the way down into the nitro group through resonance. That'll cause this factor to be actually quite prominent. And this will cause this 4-nitroaniline to be the least basic of all. Once again, we can go to some literature values to sort of check ourselves. So if we go look up the pKa's of these molecules, this is 4.6. Paranitroaniline is 1. So you see this is actually really quite acidic. This is far more acidic than a normal carboxylic acid would be, whereas normal aniliniums have similar acidity to carboxylic acids. And the cyclohexylamine is 10.6. So this trend fully reinforces how acidic the conjugate acid is to give us information about the reactivity of the parent base.